Well, hello guys.
Welcome back.
Yes, you just saw us make our own barometer. Well, we actually didn't because we changed clothes, so this is a new day, in fact, and you can be able to track our attire as we go throughout the unit. Barometer, what does it do?
So a barometer is actually a device that measures atmospheric pressure.
Indeed, indeed. And how can we make one? So this is what one looks like. Let's go through step by step. So you take a long glass tube. I'm just going to pull up mercury at, my local mart. Not sure.
So mercury is actually super dangerous. So if you're trying this at home, water.
Yes, water is what we did in here and it'll work just fine. So you get a long tube, a graduated cylinder or anything like that. You were going to fill it with water and then you're going to clog it like I did, turn it upside down and put it in the water and slowly remove your finger out so that the water is trapped in there. And I want to make sure that this water, the reason why it didn't, come rushing out is not because I trapped it against the table. That's not what happened. What happened was there's air actually holding it up. So what happened, this water equilibrates or moves down depending on how much air molecules are out here. Okay? And the lower this level goes down, so if this goes farther down, that means there's less pressure pushing down here. There's less pressure out here.
Which means that they can kind of scoot out?
Yeah, so exactly. So if there's less pressure, then that water basically can flow on out. But if there's more pressure here, so I'm going to say now there's more pressure, what's going to happen is it's going to push down on this water, which in turn pushes up on this water, which in turn
it's going to affect that gas bubble up there.
Causes this to go up. And actually, there's no gas up here. Remind me, what's this called?
Right, so this is a vacuum.
This is a vacuum, which means...
Which means that there is no gas in there.
No gas, empty area, and that's from your last unit. So this is how we can measure the different heights in mercury here. Actually tells us how much pressure is in the room. Pressure conversions, a little recall back to dimensional analysis. We've just finished stoichiometry, so you should feel pretty good about this. Just going to introduce a couple different units.
And if not, this is a great time to watch, pause, rewind, and do it all over again.
Absolutely. Okay, so 1 atmosphere. This is a new unit we're going to introduce. This is called atmosphere, and we are actually under 1 atmosphere pressure right now.
Yeah, 1 Earth, 1 atmosphere.
1 Earth, 1 atmosphere is what we got. Now this is equal to a couple different units. One is millimeters mercury, and that does in fact come from our barometer. So this is called millimeters mercury. Hg is mercury.
And that millimeters comes from the fact of you can actually measure the distance of that vacuum.
Yeah, so basically if it goes up, there's more millimeters mercury, meaning there's more pressure in the room. And this is equal to a unit called kilopascals. Okay, you've heard of kilo.
Kilo meaning 1,000. Remember, kilograms is 1,000 grams. Kiloliters is 1,000 liters.
And pascals is just an old dude's name who did a lot for science.
Easiest way to get your name in the history books.
Yep.
Discover something.
Just you guys should, because
Name
these
it
are
after
some
us.
weird names, Morris. Sellers. Conversion practice. Give me a pressure for me to convert here.
Right, so let's try 560 millimeters of mercury.
Turn off my phone. Yes, 560 millimeters of mercury. Okay, you got it. And what do you want that in?
Let's go to atmospheres.
Okay, so I want to know this in atmosphere. So I'm going to start with what I'm given. This is my given. What I know, and what I want to know is how many atmospheres. So that's what the question's asking me. So I'm going to write my given up here, come all the way across, and equals, and I want to end with atmospheres. I can set up my problem. This is what we kind of do, and I've got to get better at drawing straight lines.
But we're not art teachers.
Well, this is where I get confused. I'm like, how do I get from millimeters of mercury to atmospheres?
Well, I think we have to be able to cancel out millimeters of mercury. How do we do that?
Well, I got to put it on the bottom, which means I know I need a conversion factor. And if I can pause this and go back to the last slide, I can look up that 760 millimeters of mercury is equal to 1 atmosphere. Okay, what am I going to plug in the bottom, Miss Morris?
So that's 760 millimeters of mercury, so I can cross that out.
Absolutely. Bam. Bam.
But the top is empty.
Yeah, the top is empty, so I need to put the other side of the equation, which is 1 atmosphere. So that's where I just kind of plugged both of those in here. Okay, please notice that I did not cancel out the numbers. We still need the numbers to multiply and divide. I can only cancel out the units. Remember, everything on top, we
multiply.
Everything on the bottom,
divide.
Divide. Okay, she's got her calculator. 560 times 1.
You guys should know that. That's 1.
Yep.
And let's do divided by 760. So I get 0.736. But notice how when we first wrote it, we wrote extra and then we shortened it.
Yep. Okay, give me another pressure.
All right, let's do 790 millimeters of mercury.
Okay.
And let's go to kilopascals.
Kilopascals, I can do that. Well, maybe. We'll see. I know what I need.
With the calculator we can.
With the calculator we can, and I need a conversion factor to compare those two units. The units for my given and the units for my target are what I'm going to. So how many millimeters of mercury?
I'm guessing 760.
Yep.
Sounds about right.
And so this is 760. And this was, if we look back, is 101.3, and I can do that. 101.3, 760. Cool, cool. What goes on bottom?
Millimeters of mercury?
Yep, why?
Because I want to be able to cross that out.
Yes. Such a good student we are. All right. Boom. Boom. Which means I got to put the other thing on top.
Mm-hmm.
Decimal. And look at that. I'm left with
Kilopascals.
which is what I
want to be.
want to be. All right. 790 times 101.3.
So in my calculator, I literally have 790 times 101.3. That's 104. Okay, so I get my answer, and then I'm going to go ahead and divide it by 760. So I get 105.29.
Sounds about right. 105.29.
Real rules, and
Yep.
another slide.
Okay. So, kinetic molecular theory of liquids. These are supposed to move. They are not moving, so we have another image. But real quickly, this one right here is representing a gas. How do you know it's a gas?
Because there's a lot of distance between them.
Yeah, see how they're like, I only see two molecules here. They're moving all, they're spread apart.
Mhm.
This is a liquid. They're kind of crammed in there.
Take our word for it.
Yep, and this is our solid. And let's get a better image.
Mm-hmm.
Okay, so here we are. We've got a solid. And what do you notice about these, Miss Morris?
I noticed that they're just like soldiers, just very straight, not moving.
Yep, they're all pinned. And exactly, this is not really what a
No.
solid looks like.
Not at all.
Solid molecules, all the molecules, no matter if it's rock hard and it's not moving, you're staring at the molecules inside that rock are
Going together.
vibrating, okay? So here's what an actual solid, if we were to zoom in, here's what an actual solid would look like.
Now, do they ever look like that when they're just standing still?
Okay, we could go back. They would look like this only in one very special case.
Okay.
And that case, I want to tell you about it, is when it is absolute zero, meaning 0 degrees Kelvin. So there's a new
Wow.
unit. So this is 0 degrees Kelvin. This is like colder and cold. This is unachievable. There's no, why do I keep doing that? Kelvin. This is not achievable. Even space, which is freaking freezing.
It's still warmer than that.
Yeah, it's like 2 Kelvin, okay? So extremely cold. This is the point where molecules cease to move. This is how cold that is. But that's not actually what's going on here. This is what a real solid looks like, and you can see they're kind of just
Just shifting back and forth, but there's not a lot of movement.
bumping
No.
into each other, right? So that's what a solid is. Contrast that to a solid that's starting to melt,
Maybe heat up a little bit.
increasing temperature. And I know, what do molecules do when they get hot?
They're starting to move a little bit
A
faster.
little bit faster. So here, turn up the heat. Look at that. So they start moving like crazy, and now this is leading to a solid. Once it heats up, we all know ice is a solid, and it heats
Right.
up and it forms a
Liquid,
liquid. So we've
next
got
higher energy.
yeah. So here's a liquid. Whoa!
That is moving way, way faster.
Too fast. I bet you didn't imagine that, but a liquid water, just water sitting there. Molecules are moving at this speed, just crazy speeds. You can kind of see just watching the dark one, how fast it's moving. It's kind of the highlighted one. And if I were to take this to a liquid, now a liquid is evaporating into gas, and you can see right here that there's liquid and gas molecules are escaping, and some gas molecules are coming back into the liquid, and they're evaporating, and they're condensating. That's the word we're going to learn later. And then this is obviously
A gas.
a gas. So recap, gases, really spread out, very fast moving. Liquid, closer together,
Fast,
still
but
fast.
not as fast.
Not as fast. Solid. Oh, no, this is a liquid still. Solid.
Super packed together, really not moving that
Not
fast.
moving that fast. And this is not actually real, but we can
We like to
fantasize about
pretend.
this. Yes. Okay. Okay. KMT for liquids. Couple definitions for you. Evaporation. You've heard of this, no doubt.
So this is going from any state to a gas, remember the fastest moving energy level, but not boiling.
Not boiling. This is supposed to be working, it's not working, but what you can see, doesn't look like it's very orderly, so this is a liquid. And this one looks super orderly, so what is this going to be?
Probably going to be a solid.
Solid, they're super packed in there. And we actually have solid molecules, and they're escaping this, and they're becoming a gas out here.
Yeah, there is no in between in there.
And so this process is called sublimation, when solid goes from a gas. Can you think of an example where we have solid going straight to a gas?
I can. Dry ice. Have you seen it?
Dry ice. Wicked cool. We'll show some of that in class. That's where solid, which is carbon dioxide, evaporates and goes straight into a gas. And so there's no liquid phase. And then this is the one you're probably more comfortable seeing. You've got liquid going to a gas. Think of water boiling. Okay. What do we have on this graph? Okay.
Let's read our axes. Looks like we've got molecules going on.
And we've got number of molecules.
And looks like I'm going with some speed.
Speed, okay. And we first need to find, what is this K?
Oh, that K looks like it's a Kelvin.
Kelvin and Romy, what is Kelvin?
Kelvin is a temperature measure.
I don't know why I'm writing G. Kelvin is a temperature measure. So think of Celsius, think of Fahrenheit, they're the same thing. Just to let you know, 300 Kelvin is about room temperature.
Thereabouts.
70 degrees Fahrenheit, 25 degrees Celsius. 1,000 Kelvin is much hotter.
Yes.
So, as we can see, as this gets hotter, the average speed, it clearly increases. And then, so this one, the average speed is about 400.
It's about half that.
Half that, yeah. So, basically, the idea is higher temperature, higher speed of molecules. And think of that. I mean,
could we say that for kinetic energy?
Yeah, we can say that for kinetic energy. Higher kinetic energy, higher motion energy, if you will. Kinetic molecular theory of liquids, vaporization.
So vaporization, kind of like evaporation, but this is liquid to gas, can either be evaporation or boiling.
Yeah, so this is liquid to gas, and it can be either evaporation or boiling. Vapor pressure. Okay. Vapor pressure has a very specific definition. It's the pressure exerted by a liquid as it evaporates. So we all know gas molecules exert pressure. Remember, you are under about 14 pounds of pressure per square inch on your body right now. So those molecules are pushing against you, and we're very thankful because we've got molecules inside of us
pushing back out.
Pushing out. And if there wasn't a balance, we would either crushed or we would explode, right? Yeah, so it's a good thing. So pressure is a good thing. But we can also sense pressure in other ways. And so we've got some
rubbing alcohol. And if we open that up, and we can just actually we can't, but if we walk, definitely can smell it, right? You guys you haven't done this, but you could smell rubbing alcohol. Kind of smells like the doctor's office.
And the reason why I can smell that is because the gas molecules, so this is a liquid, there's gas molecules escaping this liquid right now, and they're bubbling out here, and then they're coming in here, and then they're reaching my nose, and those gas molecules hit the little nose hairs, and I can sense them. And if I were to boil this, there would be more gas molecules. Think of like the the liquid molecules are kind of moving, and then I increase the temperature, so they start moving more, and then I increase temperature more, and so eventually they can. One little guy escapes. He's like, I'm almost there, and one little guy escapes. And as he escapes, he comes up and he comes in my nose, and I can smell him, and so I can actually sense the pressure of the molecules. So we just kind of did that. The higher the temperature, what happens to the number of molecules that come out?
It's going to increase.
It's going to increase, which means the vapor pressure
is also going to increase.
It's going to increase. So the higher the temperature, the higher the vapor pressure. Low temperature. Look, this should be moving, but there are very few molecules coming out. Low temperature, only a couple guys, and a couple guys are coming back in, such and such and such. Higher temperature, you would see these guys, more guys going out.
And also more guys coming back in.
And more guys coming back in, that's true. Because they're equal guys going out, equal guys going in. That's called the rate of evaporation, rate of condensation. Okay?